Okay, so we've been looking at the binomial distribution. We've talked about the mean and standard deviation of the binomial distribution. We've calculated some probabilities. Um, and if you recall, I don't have it in the notes because I deleted it, but when we did this free lunch and there was 250 people, we had seen the shape of some of the binomial models. So I want to explore the shape a little bit more. So I'm going to go to this applet, have it opened up here. So this gives us the binomial model for different numbers of trials and different probabilities. So basically, if my probability is 50-50 and there's only one trial, then half the time I'll get a success and half the time I'll get a failure. Kick it up to 2 trials. Now I could get 0 successes, 1 success, 2 successes, or 3 successes. And then as I change the probabilities, it kind of changes the likelihood of each of those different outcomes. Okay, so these are all just, and this program just does it really quick and easy. For us to do it on the calculator, we'd have to create a table, calculate the binomial probabilities, open up a new graph. We'd have to do all of that. This just does it as in a snap. So as you can see, sometimes the distributions are skewed to the right. Sometimes the distributions are skewed to the left, depending on the probability. Sometimes they're kind of symmetric. As I kick up the number of trials, it kind of, as you can see, it makes it look a little bit more unimodal, right? Again, as the probabilities go really, really low, I kind of get something that looks kind of like a skewed right. If I go really, really large and kind of skewed to the left, because they're more likely to be more successes, obviously. And as I keep kicking this up, you should kind of notice something that should be at least a little bit interesting. As you kick up the number of trials, in fact, this program actually fits a normal curve to the distribution. But as you can see, if the number of trials is pretty large, it looks like the binomial model looks like the normal distribution. Now, if you kick that probability way up, it kind of will cut off the top half and it'll make it a little bit skewed to the right. So again, even if you have a lot of trials, if your probability is super, super high, it doesn't really look normal. But if you go up, kick up these trials to 100, that thing looks almost exactly normal for values from 0.1 to 0.9. But again, if you get too far up, it kind of breaks down that normal distribution. So the idea here is, as the number of trials increases, in conjunction somewhat with your probability, the binomial model can be approximated with a normal model. This is an important conclusion in statistics for reasons you'll see later. We may or may not understand them later. It gets a little bit confusing, but it's the normal model as an approximation of the binomial model is kind of a very important conclusion for a lot of the analysis we do in the second semester. I should just say it like that. So here's some specific cases. This is n equals 15 and probability is 0.1. I basically just screen captured some of these using that applet that we just looked at. So in conclusion, normal approximations for the binomial distributions. This is called the large counts condition. And it may not seem very sensible, perhaps, but this large counts condition is something we are going to check a lot later on in the semester. It's going to be one of the conditions for one of our important tests, analysis. So if we have a binomial distribution with n trials and p success rate, when n is large, the distribution of a binomial distribution is approximately normal, with a mean of NP and a standard deviation of NPQ. Well, this is just the mean and standard deviation we studied from before, but it's normal with that mean and that standard deviation. So this just says when n is large counts condition. Well, the question then becomes, how large does n need to be? And it's kind of related to the probability also. So this is a rule that some very bright mathematicians came up with. Basically, n is large enough if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. This is called the large counts condition. Basically, this is the expected number of successes. This is the expected number of failures. If those are both 10, then a normal model is a pretty good model. If these are less than 10, then the normal model doesn't work very well. That's stuff like this. And it would also be things like this. Like this is symmetric, but the gaps and the holes and the overlaps it's too chunky for the normal model to give me good approximations. Okay? So we want those spaces to be minimum. That's what the large counts condition does. And also, it'll control if it's skewed or not too. It'll prevent that from happening. Teens and debit cards. In a survey of 506 teenagers aged 14 to 18, subjects were asked a variety of questions about finance. One was, do you have a debit card? Suppose exactly 13% of all teens in the US have debit cards. So this is kind of an assumption we're making. Let X be the number of teens who have a credit card in the random sample of 506. So I select 506 kids from the population, and I look at what percent have debit cards. Okay? Is this distribution binomial? Is this a binomial distribution? Technically not. If we go to check the bins, binary, success, failure, yes, either they have a debit card or they don't. Independence, fails. Success rate, fails. We do have exactly 516s. The problem is that the percentage isn't exactly 13% each time. You know, there's maybe like, I don't know how many, 100 million, I don't know how many million people teens there are in the US, but there's a lot. There's millions and millions of teens, right? But if I take 13% of them apparently have debit cards. If you take one of those out of that population, it's going to ever so slightly change the probability that the next one is. We've talked about this before. We do not have independence. So technically, it's not binomial. Technically. However, is the distribution approximately binomial? Yes, it is. Why? That's the 10% condition. Where do we cover the 10% condition? Right here. This is another big condition that we're going to check a lot. It says, if your sample size is less than 10% of your population size. Well, we definitely have that here. So let's justify it. N equals 506 is less than 10% of all US teens. Now, I don't know how many US teens there are, but I know there's more than 5,060, right? And if there's more than 5,060, then this is less than 10% of the population. So although it is not binomial, it is approximately binomial. Okay. Is the distribution normal? No, of course not. We're talking about getting 506 kids and asking them if they're got a debit card or not. There's no way this is going to be a continuous, I mean, it's yes or no question. It's success, failure. It's not even numerical, really. No, I take that back. I'm sorry. We are recording the number of teens. So it is numerical, but it is definitely discrete. That's what I should have said. I'm sorry. Right? So it can't be continuous. It's discrete, not continuous. Is the distribution approximately normal? Yes. Large counts condition is going to pass. Large counts passes. That is N times P, which is 506 times 13%. I don't know what that is, but I guess I should do it. 506 506 times 0.13. Yeah, 67. That's plenty big. That is greater than or equal to 10. And NQ, which is 506 times 0.87, that is obviously greater than or equal to 10. So the large counts condition passes. So that means that I'm going to have one of these things here where my binomial model kind of fits really nice under that curve. And there's not very many gaps, and it's pretty much symmetric. justify. I justified it. I checked the large counts condition. So let's use a normal distribution to approximate the probability. Okay, so I have an approximately normal distribution. I want the probability that 60 or fewer teens have, so if I pick 506 kids, what's the probability that the number of kids with debit cards is going to be under 506? I need to calculate the mean. The mean is n times p. It's the mean of the binomial, which is 506 times 0.13, which I calculated up here was 65.78. Standard deviation, that's going to be the square root of NPQ. Again, binomial model. That's the square root of 506 times 0.13 times 0.87. Square root 506 times 0.13 times 0.87, 7.56. So I want the probability that it's, so this is, oh, I'm sorry, why did I put 506 here? I'm going fast because I'm trying to get the video. What's the probability that's 60 or fewer? So that's less than 60. So 65 is the average, so less than 60 is going to be kind of like right there. There's my cutoff. So let's use the normal model. Menu, statistics, distributions, normal CDF, negative infinity to 60 with a mean of, crap, what was the mean? 65.87 and a standard deviation of, is it 7.56? Last answer, 0.222. 0.222. Now, this was a normal approximation to the binomial. Let's actually use the binomial. Okay, so number of successes, now it's discrete. 0, 1, up to 59, 60, up to 61, all the way up to 506. These are all the outcomes. I want the probability that x is less than 60. No, 60 or fewer. Less than or equal to 60. Here it doesn't matter because it's a continuous model. Here it actually does matter. 60 or fewer. That is all of these added together. Sum up. That is the binomial CDF, n equals 506, p equals 0.13, lower bound equals 0, upper bound equals 60. It should be close to this. Let's see how close it is. Statistics, distributions, now go down to your binomial CDF. B, number of trials, 506. Probability of success, 0.13. Lower bound 0, upper bound 60. 0.245. 0.245. So what's my error? That minus that. So I get an error of about 2%. Now let me just point out to you that this is an approximation of the binomial, but let's not forget that this is actually an approximation of the model that has no independence. I will tell you though that this number is really, really, really close to the true value for that approximation. This is the more approximations upon approximations upon approximations. Anyway, that's how you do it.